Hello and welcome to my first video on 3D graphics on the Nintendo 64. So let's get into it. So the N64 was advanced for its time. It supported Z buffering and anti-aliasing as well as texture mapped polygons. LibDragon, which I'll be using for carrying out our 3D, has full OpenGL 1.1 support with implementation for some extensions and additions. Today I'll be going over some of the basics with OpenGL and doing this on the N64. So I'll quickly go over some bits and pieces about 3D models, and then we'll jump into some code. So first off, 3D models that are normally made of triangles, which is the simplest form of polygon. So you can think of these here as examples. The dots are kind of how they are sort of constructed on the computer. You kind of connect them together like a dot to dot, and then the computer will fill them in with either a color or a textured image, pixels that you specify to it. So the 3D models are shapes constructed from polygons. Disregard this bit about 3DS, it's the N64. Just like all other consoles and desktop PCs, a polygon is described as a plane figure made up of line segments connected to form a closed polygonal chain. In English, this just means a flat surface constructed from a list of dots or points which loop back on themselves. This is the key thing here, they have to loop back on themselves. So positioning in 3D space. So in OpenGL you can think of the orientation like this here. So we have the negative y-axis goes down, positive y-axis goes up like into the sky, positive x-axis usually goes to the right and the negative to the left. The negative z or z-axis goes off into the distance and the positive z-axis comes out of the monitor screen towards you. And then rotations, the x-axis is known as a roll, the y-axis rotation is known as a yaw, and the z-axis or z-axis is known as a pitch. So there's three scenes in OpenGL, or sorry, 3D scenes in OpenGL. There are 3 stages to set up our virtual 3D worlds. First we have to set up a viewport, which is usually related to the resolution of the screen that you are running on. So for example, on the N64 normally you would do 320 by 240, but there are other resolutions you could sort of go with. However, the higher the resolution, the more impact it's going to have on speed on the N64. So there'll be some trade-offs that you'll need to do there. And the next is we have to set up a perspective, which is how the world will kind of be drawn. So orthographic is usually good for sort of 2D, and then perspective is what we were using here, which is it has how things at a distance converge in on themselves. I'm sure you can visualize that with your own eyes. And then next we need to set up the virtual camera, where it should be positioned, etc. So let's go into some of the shapes that we can draw with OpenGL. So this is based on Legacy OpenGL, which is 1.1 is really early OpenGL. So we can pretty much draw various shapes with that. So most of the points you can think of them normally as you connect them in like local space, as in the points are related to the spaces between themselves. So if we think of like a grid here, that the points are in relation to their sort of the size of them. So I'll try and find a better wording. They are in relation to one another. Not sure if that is a better description or not. Anyway, the points are connected in OpenGL in a counterclockwise direction, and there are various shapes that we can sort of draw here. So you can either specify a fill color for a shape or a texture to use for filling the shape in. And then here are some example shapes. I'm rushing through this because I don't want it to sort of drag on. The key thing with most of this is I'll touch up on this. You might need to come back and have a look at some of it, or find some other references. Essentially, I'll provide some of the drawing code anyway for you to have a play around with, and then you can kind of get a feel from actually working with these things rather than all of the theory. This is just to quickly sort of show you how they're sort of connected. So, for example, for the drawing triangles here, you'd start at A, then to B, then to C, and then that would draw that triangle there. As you can see, it's going in a counterclockwise direction. And then we have a thing called a triangle strip, where the second triangle onwards only needs 1 point. So A, B and C is from the first triangle. You provide D, and then OpenGL takes the last 2 points to connect and fill in the next triangle, and then you would provide E, then F, then G, then H, then I, and each time OpenGL would take 2 more points that were previously supplied to create a strip. You would use this is kind of like for like terrain. And then these are examples of triangle fans. These are kind of what are used to fill the end of like cylinders and shapes like that. Or rather they were, but no longer sort of used on modern OpenGL. Like. And then these are some examples of some other shapes that is supported in early OpenGL here, where you can draw these shapes either with line segments or with like filled parts. And then note here that these positions or vectors here which you would supply would not work, because they don't connect and form like a looping shape or a filled shape as such. So one thing to note is there's a difference. There's like local and global space in OpenGL. Let's see if I can give an example. Try and clear this up with local and global space. Let's just delete all this a minute, and then we'll go for a top-down camera here. So when you're constructing things, you construct them in like a local sort of space here. So if I add in an object here, so here we have a 3D cube, and then if I bring up this information here, so the scale of, basically you make something and then you kind of keep it to scale 1. Notice that the dimensions for things can be whatever you like, but ultimately you scale this to a scale of 1.0, and then you try and always orientate the shape at location 0, 0. So if I move this, you'll see the location is changing. This here is the center, or the 0, 0 in the local space here. So you would deform everything on here. I'll move that out there and then move that down. So these sizes and everything, they are locally in respect to one another, so the formations are local to one another. Whereas when you export them, you would export them with a scale of 1. And the reason why you do all of this is you're going to later transfer or redraw this shape at various other locations in your world, and you'll be scaling that shape. So these models are basically like a blueprint for the model that you intend to draw over and over again, where you would scale this up to, say, the size of whatever in your world. This is like a local sort of sizing that you give, so all of these bits would be in proportion to whatever shape it is you're drawing. And then once you've finished, you make sure that you put the scale back to 1 for everything. Make sure the rotation is 0. And then you would make sure that you have an orientation point set at the center of the model before you exported it. I don't know if that will make any sense to you or not. It's probably something you would understand later on, but I'll touch upon it now anyway. So local space is just for when they're sort of constructed, and then you transfer them later on to global space, where you apply a proper sort of a meaningful size to them. For example, in local space, everything would in essence be like scale 1. But then when you transfer them to the world, you might want them to be 10 meters by 10 meters. So then you would have to scale them to get them to that size. Hopefully that sort of clears things up. So we'll now go into texture mapping, which is the process of instead of filling these shapes with a color, you take an image and then you map its pixels across the shape. So one thing to note about images when they are used for anything in OpenGL, basically, they're no longer referred to in like sort of pixels. They are basically become a number between 0 and 1, which makes it easy to sort of scale them. So for example, the width and height becomes 1 regardless of the actual size of the image, and then to scale that by half, you would set the width and height to 0.5. To double it, it would then be 2.0. And then normally, it's the same with colors as well. So colors are no longer between 0 and 255. They instead become a number between 0 and 1, where 1 is the full brightness and 0 would be black or the absence of color in a value. So I'll go over some limits that the N64 has. So we only have 4K as a texture memory area that the N64 can use to draw or to texture map a model. that 4K is just enough size for a 32-bit 32 by 32 pixel texture, or if you change the color format, then we can then start to work with larger textures. So there's a number of different formats which are covered in a previous video that the N64 can support. So the color which will the color format which will give us the maximum size is 16 colors. So if we use a 16 color format, we can get an image which is 64 by 64 pixels in size, or we could have 32 by 128 or 128 by 32. The key thing is that this image is pixels, when in 16 color mode, must fit inside the 4K box as well as the color palette. So some other tricks we can do is we can just create half of an image, and then when you later come to draw it on your model, mirror that image horizontally so it doubles the width of the image and gives you more detail. Or another trick you could do is this here, where you have 1/4 of an image. Obviously the image will need to be symmetrical and both horizontally and vertically, and if that is the case, then you could reuse that quarter to double the size width-wise and height-wise of that texture. So I'll now, in fact, let's go for the demo before I go for some more boring theory. So this is what the demo actually is here. So we have a first-person camera which we can rotate around using the thumbstick on the N64. We can then use the C buttons to strafe left and right, or we can go up or go down. And then what we have here is various planes and flat 3D sprites where we can bimble around. You'll see that the tree characters here are rotating on all three axes, or rather these ones. This one here is rotating on 2 axes. This one is just rotating on the Y axis here. You see we have the camera's yaw here, which is the Y rotation, which is what you use in a first person like shooter to rotate left and right. And then all of these sprites here are rotating around on the Y axis. A few of them are rotating on the X axis as well. And then a few of them have animating frames. One of them, which I just added in before I started filming this, is an example of the mirroring. If I can just find Mario a moment. Where is he? There he is. So Mario here is an example of horizontal mirroring here, as the texture for him is actually 32 by 128 pixels in size, and he's constructed of 2 flat 3D sprites. So I'll now sort of touch on how these are sort of drawn here. Like, so this is an example of what I was saying about local space here. If you could imagine like a grid starting at 0 and then going positive on the x-axis, and then this is the negative x-axis plane here, positive y-axis and a negative y-axis, and then you plot the points in a counterclockwise direction. So if we wanted to draw this triangle here, then we need to provide each of these points into a GL vertex command, and then the order you specify them is the X, the Y coordinate, and then the Z coordinate. As you can see here, this is just on the X and Y plane, so this would be kind of like facing you, like the 3D sprites, and then these would be the points you would use here. So these sizes are local sizes, and this, by having them between 0 and 0.5 and minus 0.5, just means that the center will be at 0, 0, and when we rotate it, it will rotate around its center. So this is an example of the 3D plane, which is what I was using to draw the floors. So the floor plane is on the Z and X axes, as it has no height. And then the coordinates we would pass in for this here, as you can see, it's just on, so 0, 0 is actually the bottom. Well, in this appearance it would appear to be bottom left here, but in fact it would be sort of like bottom toward you. And then again you would go in a counterclockwise direction with the 4 points, and we specify like a quad type, which is a square or rectangular shape, to draw this here. And then this is the shape which was used for all of these 3D sprites, or billboards as they're known. So one of the things I did here was, instead of centering it on the y-axis at 0, I instead put the origin at the bottom center, so that I could easily position it on the floor of the world, or rather the sort of like virtual level or scene, if you like. This means that it can rotate around on the y-axis, which is rotating around the center there, fine. However, if you rotate it on the X or Z axis, then it will be rotating in relation to the bottom here. And that's all of the stuff here in this slide that I wanted to cover. So we'll jump into some of the code now and how this works. In fact, what I'll do first is I'll explain how you can convert some of these images to use. So if you got your image that you wanted to use, say we was going to use this. So if I bring this across here, I don't know how many colours that's got in, it's probably got a load of them. So this is too big for us to work with, so you want to copy this, and I would recommend that you get the GNU image manipulation program, and then we can paste this in here. And then if you go to colors and then go to image mode precision, mode, go down to index and then select 16 colors and convert, and now that's converted to 16 colors. Now you can copy that back into LibreSprite, put it in a new frame, and then Give it a name like that. And then what we want to do, I think it's that one there. I just saved. So if you open up your project, so I'll assume that you've watched the 2D examples. So just like loading normal 2D images, you put them in your assets folder. So we'll copy and paste that one in here now. Then we'll side by side these. And then to load in this image, first off you want to note it in your make file. And the reason why we need to do this in the make file is because we have to specify this color format here, which is the 16 color format. Otherwise it will not work, as there's too much detail in here. The size is too big. And then in this case, I think it's 64 by 64. And then just specify your size in there, just so the Make Sprite program knows what it's actually doing. And then in here I have a list of all the assets I'll be working with, as the makefile obviously converts them and puts them in the virtual file system, but you still then need to load them in. And then you also want to make note of this order here as well, which is what I do here. So what we do now is, now we have the asset name in there, we also want to make a note of the texture in here. So what should happen now, I've got another enumeration here, so we will add that one in here as well now. And then we'll build this. Okay, that's weird, the floor has been picked up. Something not quite right there. Looks like I should have enough here. Oh, I know why. I've got a construction bit here for the various types here. I'll get into some more of this in a moment. I wasn't given this actor a texture, so it was picking up texture 0, which is the floor. I'll jump into this in a moment. There we go. There he is. I think it's from Ghostbusters, that one there. So bimble around, try and see if we can find him. Come on, where are you? There's a random sort of movement on them just to make the demo more interesting. So loading the textures in is very straightforward. So where has it gone? So one thing to note as well is the depth checking has been disabled for the 3D sprites, which makes them kind of act a bit weird here. You'll see that the girl character, some of them sort of are actually behind one another, but because of the draw order, they appear in front still. Anyway, that character is here somewhere. So that's just an example of how easy it is to add in extra stuff here. So let's see where to start. So I've gone over loading how to arrange the like assets for them. So we have let's start at the beginning here. So some other things I'll note here as well is I've recently updated to the newest preview branch, LibDragon, and it broke all of my old programs, as it's now included these other parameters to the resolution T structure here, and didn't note anywhere that it had actually done that, which was useful. And every time a program started, it would crash with a floating point error. So if you're getting that, it's because these parameters on this new structure need to be set to 0. There's the ability now to set the aspect ratio for 16:9 sort of HD TVs if you want to do that. And then if you rebuild the project, you'll see that it's been letterboxed now. LibDragon's done that for you. It's added like black lines top and bottom, and the aspect ratio has been stretched out for like HD TVs. However, it's kind of at the expense of some of the vertical scan lines. As you can see, some of the text is now slightly distorted. Just thought I'd mention that there. So just like on the 2D demos here, first off, you need to initialize the image manager code. So the previous image managers code in the 2D demos had this structure here. I'll still keep it here for like fonts. If we have a look in here, you'll see we have a background image. So that's something you could have a play around with. So where are we here? So you see we've got background 1 there. I did have another background. Let's let's find another background a moment. There we go. A scarier scene here for you. So with the background, you can, if you draw that first before you start the OpenGL drawing, and before you enable the OpenGL context, then you can quickly draw some 2D before the 3D begins. So let's go over, so in the image manager, this handles the textures as well. So we have an image list and a texture list or array. There is a variable which holds the active texture ID, so we are not calling bind texture over and over again if we already have it as the active texture. So there's a few things to note in here. So our sprite types are what hold the actual graphics, and then these other parts here are for use by the OpenGL drawing code. So one of the things I've put in here for the draw floor is the ability to scale the UVs. So as I said earlier about texels being from 0 to 1 on an image, if you set up OpenGL to enable texture repeating on a texture, then you can kind of scale that texture across the whole size of the model or mesh that you draw. When we draw the floor, in the draw floor function in here, we are scaling the texture of the floor by 2. So if I go over the top there, set that to 10 and then rebuild that, I'll quickly show you that. You'll see that the floor terrain now is now highly detailed. It hasn't really had too much of an impact on frames per second, which is good, and it gives us the ability to have a more detailed floor without us having to draw more. So that's a nice little enhancement you can have there. put that back to 2. By all means, have a play around with that with whatever floors you want to chuck in. So I'll get back to the image manager here as a so when you add a texture, or rather when you load in one of your textures, you pass the texture name, which is from your textures list, and then you say whether that texture should be a repeating texture. Ideally you want a seamless mirrored texture to do that with, and then all what happens in the load texture function here is it stores the repeat into the texture that it's about to load. It just says that it repeats, and then note here this command here for working with the GL sprite textures here. This allows us to set the textures S and T UV parameter to repeat. Otherwise we set that to 0 and then say that the texture doesn't repeat. And then some other things you can play around with as well is how the textures should scale. So the texture parameter for maximum scaling is a mag filter. You can either go for linear or nearest. So this could be quicker, I'm not totally sure, I haven't double checked the speed differences. I think there is a minor difference, but I think what it means is that the images won't be so pixely if you use linear scaling. I think you can definitely notice it on the floors, I think. So this is one thing that the N64 had over the PS1 at the time, was the ability for different filtering. So linear gives you the best scaling, and then all what happens in here is once the image is loaded, we have to go through the normal OpenGL process of generating a texture ID, and then you have to bind that texture before you can work on it, as is normal with OpenGL. I'll give you some links to some useful videos which I have used in the past and still use to brush up myself on Legacy OpenGL. There's a channel called the C++ Guy, which has some nice Legacy OpenGL videos. They are very dated, but then so is Legacy OpenGL. So that's how we load our textures in here. So always call the initialize function in here first before doing anything, as this sets the image count to 0, the texture count to 0, it loads some 2D graphics first. Just the fonts basically. And then it obviously says that it's the image manager is initialized there, and it also sets the active texture ID to -1. This is so that we don't try and do everything when the image manager is not initialized. So at the start there will be no texture bound, and then there's a few error checks in the bind texture function here. So that's the image manager, the two most important function, or the two important blocks of code after that are the 3D, scene 3D here. So I'll go over what we've got here. So I did have a lot more functionality in here. I don't need that, I'll move that. So the structure for working with the 3D sprites, this here makes it easier to do. And then there is one function here for drawing the floor, and there's one for drawing a normal sprite, and one for drawing a mirrored horizontal sprite. Another thing that we do as well before drawing the sprites, disable the depth checking and then enable it afterwards. So let's go over some of the drawing stuff here. So as I was saying in the slides here, this is the draw code here for drawing a floor quad. So the GL vertex 3F, this is the dot or position of one of the points that makes up the quad. This GL texture coordinate passes where or which texo to associate with that point. And then I'm passing in these normals here, but there isn't actually any lights used in the scene. They usually specify how lights work or should work when they hit a surface of something. I would just leave those in for now. These usually are perpendicular to the face. So for the, as these are the floor, all of the normals are exactly the same. They all point up on the y-axis. This is where, if you can envision a loco space, if you can think back to those grids I was showing earlier, where the positive y-axis goes up, all of these basically are pointing up into the sky. All of the floor vertex are either on the X or the Z plane. And then everything works on two matrix pretty much. In OpenGL we have the model view matrix and the projection matrix. So the projection matrix is taken care of in the camera structure here. So in OpenGL, to work with the camera, or rather the perspective, we use this function called GLU perspective, and it takes a few parameters: the field of view, the aspect ratio, which is the relationship between the width and height sizes, just divide one by the other, and then you specify a near plane value and a far plane value. This is just how close a 3D shape gets to the lens of the camera before it's clipped, and this is how far you can see before a shape is clipped. And then in the camera structure here, we hold a position of our camera, another vector 3, which is contains an X, Y and a Z value of where the camera is looking, and then we have our X, Y and Z rotation angles. So when we set up, we call the image manager initialize first, then call S3D initialize, because in the S3D, where are we here? Oh, it's setting up the I probably should rearrange some of this. I didn't realize I was duplicating it all. So we need to call the camera initialize code in here, which sets up the projection matrix using this function here, GLU perspective. It then just jiggles our camera about and then calls the update function here. So these move X and move Z commands here, these are what allow the camera to move around. You pacify how the speed of the camera, its strafe, and then using trigonometry functions here, it works out what orientation the camera is pointing, and then updates its position with the speed, the strafe, and the yaw angle of the camera. And then you usually have to call one for the X movement and one for the Z movement. You could put them both together, but later on, if we wish to check for collisions with other objects, which we will, you have to split them. Otherwise, you will not be able to get slide-in collision with other objects otherwise, as you need to sort of, this just moves the X position of the camera, and then this just moves the Z position of the camera. So you kind of need to move one first, check if it's collided with something. If it has, reset it, and then do the same with the Z axis, which is why it makes sense to keep them split like this. So at the start we set the position, the angle and everything. We then call these to move with a speed of nothing. This just makes sure that the angles, the position and everything are recalculated at the start. And then after that you call the camera update function. And then what this does is it sets the model view matrix, which is what is used to draw the various meshes in our 3D scene in relation to the camera. And then the GLU lookup function here this takes the first three parameters here are our camera's position. The next three is the place we are looking, and then you have to pass in three parameters which specify the op vector. Just always pass in 0, 1, 0. This just says that positive y is op, and that's all I'll sort of cover here. Like, lots of this you can just play around with without actually knowing what all of this does, and just have a look at the various Legacy OpenGL sort of tutorials to try and figure out if you are not aware what these actually do. Playing around with trial and error is obviously really helpful. If you sort of struggle with some of the theory behind some of it, which isn't something that I sort of picked up in one go myself. Loads of this I kind of just used as it was before I got comfortable with what all of this sort of does. So the S3D initialize stuff here, this sets up our I don't need to include that there. This sets up our projection matrix and our model view matrix. So one thing to note as well is by all means have a play around changing the field of view, the near and the far values, if you want to see what effect that all has. And then we just pass in some basically some starting parameters for how OpenGL should work. Lots of this stuff, just set it up once and then you just sort of leave it as it is. So this one here just gives some hints to smooth polygons, and then there's another one here for perspective correction hint. So for all this stuff, if you right click on this, you'll see there's a whole list of GL stuff in here. It's worth noting that although all of this is here, not all of it is actually supported. So this is the various OpenGL functions in here. So all this does here is we basically say enable texture mapping, enable co-face, which just says we want to only draw like front faces. That will make no real sense to you until you sort of get into OpenGL more. And then we also want to enable depth testing as well. And then we also want to enable normals to be used. And then this clears the depth buffer at the start. And then we want the shapes to be drawn smooth. I think you can specify flat. So we'll pass that in, and then I don't know if I've actually looked at that before. Not sure what difference this will actually make. Okay, oh yeah, always make sure that is at the start there. Yeah, you're probably not going to notice the GL flat, to be honest, because we're only working with flat planes. But if you were drawing like spheres and cylinders and rounded models, it would probably stand out more, as we don't have any curved surfaces. It's not really going to affect us here. So call this at the start, and then always load the textures after you've initialized the GL core and the texture manager. And then this just goes through the asset name list here, and then this is at the bottom of the texture's name here, as it's just used to catch the end of our list. And that's that. And then there's a S2D, and it should be called. Okay, I don't know why that wasn't called. So make sure you initialize both of these first off, and then we add in some font sets here. This was covered in some of the previous videos, so I won't go into any detail on that here. And then we link in the 3D stuff to the S2D get display and S2D render stuff here. So this here, this S3D is context active. We only want to do any drawing if S2D has got the frame buffer. So if we go into what this actually is, so what I'm doing here is we need to get basically a frame buffer, the surface T type from LibDragon, so we can do our rendering. And then if we are able to get that, the extra step we take is we also now get an additional surface, which is the Z buffer for working with 3D. And then we attach both of these, and then in the render part here, if we have an active frame buffer, then we draw all the 2D stuff last, and then we detach and show both of the buffers basically. So those are the changes in the S2D stuff. And then you'll note here that anything you want to draw behind the 3D scene, you can draw before the S3D render start is called. And then this here needs to be before the S2D render command here. I don't think there's anything in there at the moment. Oh yeah, there is actually GL context end. So once you kind of get the context for the OpenGL layer, then you do all your 3D, and then once you've finished for that frame, you then GL context end, and then in S2D render it then does all of the remaining 2D stuff, so that the 2D is drawn above the 3D layer. So you can use that for like heads-up displays, all that sort of good stuff, as well as debugging text. And then that's the main loop there. So in the so let's go over the render start function here. So what we have in there is you call the GL context begin. We set the context to active there, so that in main it knows that OpenGL is active, so that it can pick up and release the context after we've finished drawing everything. So one thing to note in here is, because I am drawing that background, I don't clear the color buffer, as drawing that background will do that for us. If you don't want to draw a background, then comment that out and then you want to add that back in, which is the normal in most normal OpenGL stuff, where we have a clear color instead, which is blue in this case. Again, as I was saying earlier, this clear color here, we have a red, green, blue and alpha value. And like I was saying, the color ranges are between 0 and 1.0, with 1.0 being full brightness and 0 being black. So if we pass in 0 for red, green and blue, then obviously this will be black. As you can see there. However, I think the backdrops work better. So once we've cleared everything here, camera update is called in the S3D render code. And then this just works out the model view matrix at the start. And then we set up all of the OpenGL parameters ready for drawing our scene here. This here is important. This function here sets up how textures interact with one another. And then the other thing to note in here as well is the reason why we call push matrix first whenever we draw something is what this will do is it will push the model view matrix onto the matrix stack. And the reason you want to push and then pop that each time you draw something is the translate and scale commands actually work on the current matrix in there. So they are all kind of in relation to the model view matrix. So you always push and pop that which you will already know if you work with if you've worked with any Legacy OpenGL before. And then in the sprite code, it's basically exactly the same as the draw floor code, except we're not mucking around with scaling the UVs in here. Instead, they are literally just between 0 and 1. So the sprite code, the sprites are literally drawn on the X and Y axis, which you can see through here. They have no Z depth, hence the scale here scales the X and Y only and leaves Z as 1. And then the order you carry out these commands in are important as well. So you always translate first, and then you rotate, and then scale at the end. By all means, have a play around with these to see what differences they'll make. And then the draw mirror sprite, instead of minus 0.5 to 0.5, the first half is between minus 0.5 and 0. So this is kind of drawing two planes or two quads next to each other, and they literally reduce the size here. So instead of drawing the faux minus 0.5 to 0.5, we draw half here using the normal text coordinates, and then this draws the other half from 0 to 0.5, and then we mirror the X texel coordinates and that's pretty much all that I'll be covering in here for this video. The next video I will introduce using display lists, which is a faster way of drawing models and shapes. This here is known as immediate mode and is a slightly slower process when using display lists, but obviously I didn't want to chuck too much stuff into this demo stroke tutorial. So the in the actual sort of demo here, I've created like a virtual sort of mini level here, and then these types here refer to the numbers in here. So anywhere there's a 1, that's a tree. So I've just specified the world size as a 10 by 10 grid here. By all means expand that, have a play around with it. And then I've created a mini actor type here, which contains one of the sprites here with some useful stuff in here to work with them. The girl animations, where is it? Let's get to our assets folder here. You'll see there's 3 frames for her walking here. There's 2 animation frames for the fly, but the girl animation frames, so the first frame has her with her left leg forward. Frame 2 has her with both feet in place, and then frame 3 is literally this here. So this is how you would kind of handle the animation frames. For like a complex animation, you might create like a whole list here, and then the way that this is organized, we have like the base animation texture. So this is like the starting one, and then the animation frame offset just takes these numbers and adds it onto the base texture ID. And then these parameters here just have like them. If you change the size here, you might need to update the numbers for the maximum amount of actors or the maximum amount of trees. These are the actor types. And then this just initializes the level here. It just scans over the map at the start to figure out what's what, and then it just populates the lists, whether it adds a tree or an actor. If the type it finds is an actor, then this just sets up some parameters at the start for each actor type. Nothing magical there. And then we have one function for drawing our floor. So you'll see that the z-axis goes from 200 to 700, but it's actually going in the negative z-axis. I kind of usually orientate everything in the worlds I create so that they start at 0 and then go forward. So if you think of this map here, this tile here will be drawn at 0, 0, and then it works down here. So that would be minus tile height. So this would be at minus 50z by 0x. Then it would be, the next one here would be minus 100, minus 150, and so on. So this just draws one floor tile. This is just basically, it's kind of filling out the area underneath where the walls, which in this case would be like the trees, will be drawn. And I don't pass in a texture for the floors here. If you notice in here, there is no parameter to set the texture, and it's because usually when you draw in a floor, they're probably all going to be the same. So I would just bind one texture beforehand and then draw all the tiles for the floor. I did try using just one large floor plane, but the OpenGL engine was kind of glitchy and the clipping wasn't quite right. So play around with all that there. And then this here is just the a function which incorporates drawing the whole map. This just draws the trees. This bit here draws all the actors. And you'll see here we have enable 3D depth checking and disable it here. Nothing too magical going on. Just note here that all drawing should be only done when the update display now setting is active. So when that's active, then we can do all the drawing, draw the map, print some text, and then read the thumbstick here. and then use the C buttons here. And some other useful stuff here. There's a wrap angle function in here. There's some functions to set up the vector free F type. And I won't be covering this function here in this video, but I'll leave it there anyway. And one thing to note is some of the maths functions here are using a fast math header, which is supplied by LibDragon. And I think this is it for this video. It's already probably been quite long, so hopefully this will prove an interesting stepping stone for you to get into. Let me know if you've got any questions in the comments below, and I might be able to answer them. So thanks for watching, and I will catch you in the next video. The source code here will be linked below. Thanks for watching.